4 billion years ago, you could have stood on the surface of Mars and looked down at a river. Not a seasonal trickle, not frozen permafrost, a real river, flowing under a blue sky, cutting through red rock, emptying into an ocean that covered the northern hemisphere of an entire planet. You could have cupped your hands and drunk from it. Mars was not always the red, dead, silent world we see today. It was warm, it was wet, it had weather, it had seasons. And by almost every measure we understand about habitability, it qualified. So what happened? Something killed Mars. Something so thorough, so complete, that it stripped away the oceans, tore off the atmosphere, and left behind nothing but a frozen, irradiated desert the size of all of Earth's landmass combined. And here's the part that should keep you up at night. The same thing could have happened to Earth. In fact, by the odds, it should have. So why didn't it? To understand how Mars died, you have to go back to before either planet existed at all. 4.6 billion years ago, there was no solar system. There was a cloud, a vast spinning disk of gas and dust and ice, slowly collapsing under its own gravity around a newborn star. And in that disk, something beautiful happened. Grains of dust began to stick together. Pebbles became boulders. Boulders became mountains. Mountains became planetesimals, the embryos of worlds. Within the inner solar system, 4 of these embryos survived the chaos of the early collisions to become the rocky planets we know today: Mercury, Venus, Earth, Mars. And in the beginning, Mars and Earth looked almost identical. Both formed from the same family of rocks. Both developed iron cores at their centers, surrounded by a mantle of silicate rock. Both were bombarded by asteroids and comets during the late heavy bombardment, a period so violent that the surfaces of both planets glowed red with impact craters. And crucially, both developed oceans. Scientists now have strong evidence that Mars once had liquid water covering roughly 20% of its surface, a northern ocean deeper than the Mediterranean Sea. We found the ancient shorelines. We found the river valleys that fed it. We found the delta fans where those rivers met the sea. On Earth, we look at these conditions and call them habitable. On early Mars, they were identical. So, at year 0 of this story, 2 twin worlds orbit the same star. Both warm, both wet, both protected. The stage is set for life on 2 planets simultaneously. Then the paths diverge. For about 500 million years, roughly from 4.1 to 3.7 billion years ago, Mars was, by scientific consensus, a genuinely habitable world. Let's be clear about what that means. The early Martian atmosphere was thick enough to create a greenhouse effect, thick enough to trap solar heat and keep liquid water stable on the surface, even though the young sun was 30% dimmer than it is today. The pressure at the Martian surface was comparable to standing at altitude on Earth, something like the pressure at the top of a mountain. Not comfortable for humans, but not instantly lethal either. And there was a magnetic field. This is the detail that most people miss when they think about Mars. Earth's magnetic field, generated by our churning liquid iron core, is what deflects the solar wind, the constant stream of charged particles that the Sun fires in every direction at 400 kilometers per second. Without that shield, the solar wind strips away the upper atmosphere like a sandblaster. With it, those particles curve harmlessly around the planet. The atmosphere survives. The oceans survive. Life has a chance. Early Mars had that shield. The ancient rocks on Mars, the oldest ones from over 4 billion years ago, are magnetically striped. Just like the seafloor on Earth, those stripes record the direction of the magnetic field at the time the rocks solidified. They're the geological fingerprint of a working planetary dynamo. Mars's magnetic field wasn't as strong as Earth's, but it was there. Auroras danced over its poles. The solar wind curved around it. The atmosphere held. For 500 million years, Mars was protected. And then the dynamo stopped. This is where the story becomes a murder mystery. Roughly 4 billion years ago, within a geologically short window, perhaps just a few million years, Mars's global magnetic field collapsed. The planetary dynamo switched off. We know this because the younger rocks on Mars show no magnetic memory at all. The stripes simply stop. One layer, there's a field. The next layer, nothing. Mars's magnetic history goes silent and stays silent for the next 4 billion years to the present day. So what killed the dynamo? To understand that, you need to understand what makes a dynamo work in the first place. Deep inside a planet, a magnetic field is generated through a process called the geodynamo effect. When electrically conductive fluid, in Earth's case liquid iron, moves through convective currents in the outer core, it generates a self-sustaining magnetic field. It's essentially a massive, planetary-scale electric motor made of molten metal. But that convection requires one thing above all else: heat. The iron has to be hot enough to stay liquid, hot enough to keep moving. The temperature difference between the inner core and the outer mantle has to be large enough to drive the circulation. And heat on a rocky planet is finite. It comes from two sources: the residual heat left over from formation, the energy of all those primordial impacts, and the slow radioactive decay of elements like uranium, thorium, and potassium inside the planet's rocks. Both of these heat sources fade over time. The question is, how fast? And that's where Mars made a mistake it was born with. Mars is small. Not just a little small, half the diameter of Earth, 1/10 the mass. And that size difference, that single accident of birth position in the solar disk, determined everything that followed. A smaller planet has a higher surface area to volume ratio. In simple terms, it loses heat faster relative to how much heat it contains. The same way a small cup of coffee cools faster than a large thermos. Mars, being half Earth's size, cooled dramatically faster. Within the first 500 million years, the heat that powered the convective churning of its iron core had bled away into space. The iron solidified, the circulation stopped, the dynamo turned off. And with the dynamo off, the shield went down. Once the magnetic field collapsed, Mars's death was not instant. It was slow, methodical, relentless. The solar wind, that stream of charged particles hitting the planet at 400 kilometers per second, began to interact directly with the upper atmosphere. Without the magnetic field to deflect it, the solar wind tore into the ionosphere, ionizing gas molecules and giving them enough energy to escape Mars's gravity entirely. Atom by atom, molecule by molecule, the atmosphere began to leak into space. And at 4 billion years ago, the Sun was also more active than it is today. Solar flares and coronal mass ejections, enormous eruptions of plasma, were more frequent and more violent. Each one delivered a concentrated burst of stripping energy directly to the unprotected Martian atmosphere. Scientists using NASA's MAVEN spacecraft have actually measured this process happening today. Even now, even with Mars's thin modern atmosphere. MAVEN found that during a single large solar storm, the solar wind strips away the modern Martian atmosphere at roughly 100 grams per second. That sounds small, but multiply it across millions of years. Multiply it by a young sun that was throwing off far more intense events, and you begin to understand the scale of what Mars lost. It took roughly 500 million years for the atmosphere to thin to a critical threshold. As it did, the greenhouse effect weakened, temperatures dropped, the liquid water on the surface began to freeze. And as it froze, something paradoxical happened. The carbon dioxide that was keeping the planet warm began to be absorbed into the ice and rock. The greenhouse effect weakened further. The planet cooled faster. More ice formed. The cycle accelerated. Scientists call this a runaway glaciation feedback loop. Once it starts, nothing stops it. The rivers slowed, the Northern Ocean shrank, shorelines retreated inland. The sky changed color. From blue, yes, early Mars likely had a blue sky, to the thin, hazy pink that Mars rovers photograph today. And the water didn't just freeze. Much of it was photo-dissociated, broken apart by solar ultraviolet radiation, now unblocked by the collapsed atmosphere, into hydrogen and oxygen. The hydrogen, being the lightest element, escaped to space. The oxygen bonded with iron in the surface rocks. That's what makes Mars red. It's rust, oxidized iron. The literal remains of water chemically combined with the planet's surface. Mars didn't just lose its water became the planet itself. So why didn't Earth die the same way? The answer is almost uncomfortably simple. Earth is bigger. Not dramatically bigger, not Jupiter scale bigger. Earth is only twice the diameter of Mars. But in planetary science, that factor of 2 is the difference between life and death. Because Earth is larger, it formed with more radioactive material locked in its rocks. More radioactive decay means more internal heat generated over longer timescales. Earth's core has stayed hot enough and is still hot enough today, 4.5 billion years later, to keep the outer core liquid. And a liquid outer core means convection, and convection means the geodynamo effect. And the geodynamo effect means a magnetic field. And a magnetic field means an atmosphere. And an atmosphere means oceans. And oceans mean, possibly, us. But size alone isn't the complete story. Earth also had one more critical advantage that Mars lacked: plate tectonics. On Earth, the crust is broken into roughly 15 major plates that move, collide, subduct, and recycle constantly. This geological conveyor belt does something essential. It regulates the carbon cycle. Carbon dioxide in the atmosphere dissolves into rainwater, which erodes rock, which carries the carbon into the ocean, which deposits it on the seafloor, which gets subducted back into the mantle, which gets released again through volcanic eruptions, completing a loop that has kept Earth's temperature remarkably stable for billions of years. Mars has no plate tectonics. Mars has a single, solid, unbroken crust that stopped moving early in the planet's history. When volcanic outgassing released carbon dioxide, there was no efficient way to cycle it back. And once the atmosphere thinned past a critical point, no amount of volcanic activity could rebuild it fast enough. Earth's geology is self-correcting. Mars's was not. And there's one more factor, one that brings us back to the previous video in this series. Earth has a large moon. The moon's gravitational interaction with Earth helps maintain the slow, stable rotation rate that keeps our geodynamo efficient. It contributes to tidal heating within Earth's interior. It stabilizes our axial tilt and thereby stabilizes our climate. Mars has 2 moons, Phobos and Deimos, but they are tiny, irregular captured asteroids. They exert essentially no stabilizing influence. Mars's axial tilt has wobbled chaotically over millions of years, between 10 and 60 degrees, contributing to its climate instability. Earth got the size. Earth got the plate tectonics. Earth got the moon. Mars got none of them. And Mars paid for it with everything. Here's the thought experiment that haunts planetary scientists. What if Mars had formed just slightly closer to the Sun, say in the position where the asteroid belt now sits? At that distance, more material would have been available during planetary formation. Mars might have accreted to double or triple its current mass. Large enough to sustain its internal heat for billions of years. Large enough to maintain plate tectonics. Large enough to hold onto its magnetic field. The models suggest that a Mars with twice its current mass might still be warm today. It might still have an atmosphere. it might still have liquid water. And if it had liquid water for 4 billion years instead of 500 million years, the same 4 billion years that produced complex life on Earth, the question of what might have evolved there becomes genuinely unsettling. We keep searching Mars for signs of ancient microbial life. We drill into its rocks. We analyze its chemistry. We look for biosignatures in its soil. But what we rarely say out loud, what planetary scientists whisper to each other at conferences, is that Mars may have had enough time for life not just to start, but to become complex, to evolve, to differentiate. 500 million years was enough on Earth for life to go from chemistry to single-celled organisms. We know that. We have the evidence in Earth's oldest rocks. 500 million years on Mars, same chemistry, same water, same energy sources, may have been enough for the same thing. Whatever it became, it died. It died when the magnetic field turned off. It died when the atmosphere was stripped away. It died when the oceans froze and the water left. And we have spent decades and billions of dollars sending robots to find even a trace of it. The story of Mars isn't just a tragedy about a dead planet. It's a data point, the most important data point we have about how rare the specific conditions for long-term, complex life actually are. In our solar system alone, we have 4 rocky planets in the inner system. One of them has complex life, Earth. One of them, Mars, may have had simple life and then lost the conditions to sustain it. 2 others, Mercury and Venus, never had the conditions at all. That's a 25% rate for briefly had the right conditions, maybe less for actually produced life. And that's in a solar system where we got unusually lucky. A stable G-type star, a giant planet like Jupiter in the outer system that deflects incoming asteroids, a large moon, plate tectonics, the right size in the right orbital zone. Remove any one of those factors, and Earth might look like Mars today. The reason this matters is the Fermi Paradox. The universe is 13.8 billion years old. There are 2 trillion galaxies. Within those galaxies, there are hundreds of billions of stars similar to our Sun, many of them billions of years older than our solar system. If life emerges wherever conditions are right, and if complex life is common, the universe should be full of civilizations. We should be hearing signals. We should be detecting artifacts. We should not be alone. We are alone, or at least apparently alone. And Mars tells us why. The window for life is narrow. The geological conditions required are specific. The size has to be right. The orbit has to be right. The star has to be right. The moon has to be right. The plate tectonics have to work. The magnetic field has to last. Change one variable and you get Mars. We didn't just get lucky. We got lucky over and over and over again. If this video made you look at Earth differently, subscribe.